All right. So I'm going to give a couple minutes for everyone to come in and settle down. I know we had a couple people parking and we have a scouting group here, so I'm going to give everyone here a minute to settle down. But welcome to United Astronomy Clubs of New Jersey. We are here once again at our observatory in Jenny Jump State Park in Hope, New Jersey. So welcome to those who are not only joining us here, but also online, because that is right, we do live stream these every Saturday to Twitch and YouTube. So if you're ever looking for something to do on a Saturday night because your plans have fallen through, you can always join us online and say hi to me in chat, because I do monitor that through my portable internet device. In addition, you should definitely check us out on our website, uaznj.org. It's where you're going to find a list of all our member clubs, because we are a club made up of other clubs, and some of the easiest ways to get into astronomy is actually to join your local club. They're going to find, in addition to being the closest one to you, and therefore usually some of the easiest to get to, they're going to have tips and tricks of like the best places to view various things in your area. That, for example, tips I know for out here in Warren County, New Jersey, might not be the best for those looking in New York City. And we do have a number of clubs in New York City who are actually part of us. So like I said, do check us out on our website. In addition, you can check us out on our social media, our Facebook, Instagram. We have a Discord server, all great places to get in touch with us, find out what's going on, as well as ask any questions you have, or even just share your astronomy pictures. So, since it looks like we're all here and settled down, you guys here get to hear the safety briefing. If you need to use the restroom, that is the porta potty in black. It is in back. It is big. It is blue. At the nighttime, you will see it is illuminated by red, because I actually remembered to turn on the light switch today. Yeah, my fiance gave me a lecture about that. You can't say you can find it in the dark with the red light if you don't turn the red light on. Oddly enough, he is correct. We also have a little museum area and gift shop. I will be manning the gift shop after the talk, because I still cannot break the laws of physics and be in two places at once. That is strictly forbidden here. We do have to obey all laws of physics among them. So usually after the talk, we have observatories open and we have stargazing. I pray and hope that we have a clearing where we could show you, but if we don't, I do believe we have
a couple of scopes open, especially for the Boy Scouts who might want to tick a couple of, Cub Scouts want to tick off a couple of boxes for their requirements. You can poke your head in and see a scope and maybe discuss with one of our volunteers what the scopes are about. However, it being sensitive equipment, we don't want to expose it to the weather, so we're not going to be able, if it is at all even dripping like a little bit like it is now, or there's just nothing in the sky to see, we're not going to risk opening the observatories.
In addition, for those of you who drove here, since some of you hiked up, I think, I know a number of you drove, when you do go home, do use your headlights. We do not like getting run over. I'm sure you also feel the same way, that running over is something you would like to avoid in your life. Use your headlights. We greatly appreciate it. It does get dark here. It is a state park, so there is less light pollution than normal. So a number of you may be using flashlights or your cell phones or whatnot to get around. I do ask, if possible, we keep those pointed towards the ground, just for the fact we don't need to have any lightsaber raves where we accidentally blind people looking into the super bright flashlights. It's no fun, so let's avoid that when we can. So I think that covers all of our safety briefing. And you are not here to hear me blabber on for forever. You're here to actually hear Paul.
Blabber on forever.
He's more educated and informed than I. Paul Fischer is going to give the talk Bang, Woosh, Zoom tonight He has a Bachelor in Engineering in Chemical Engineering from Stevens Institute of Technology and has worked in environmental and chemical industries. Though always interested in celestial objects, Paul's official start in amateur astronomy was one night several years ago, lying in an awkward position on his roof in the freezing cold holding a pair of binoculars. He caught a brief clear glimpse at the Galilean moons of Jupiter and was hooked. After introductory reading that puts all of our to-be-read list to shame, he purchased his first telescope and is now an active member of Northwest Jersey Amateur Astronomers and volunteers here at United Astronomy Clubs of New Jersey, and still manages to find himself outside at night in awkward positions in the freezing cold during the winter, seeing or the absolute sweltering heat
sometimes
and humidity we have now. Seeing neat stuff in the sky outside.
Thank you, Kim. Hello, everyone. As Kim said, I'm Paul, and tonight's presentation is Bang Woosh Zoom. Any guesses on what the... and it has nothing to do with Ralph Cramden. Nothing to do with Ralph Cramden. Go ahead. Make a guess. You don't know. That's okay. You don't have to know. What's that? You don't know yet. Well, I'm going to tell you right now. It's the Big Bang Theory, obviously. Maybe in retrospect, the Big Bang Theory maybe sounded something like Bang Whoosh Zoom if you could put the light data to some sort of sound file. And maybe we're going to go into that, why it might sound like that in a little bit. This is a slightly irreverent book report on the first 3 minutes. So I am an amateur astronomer. I leave the actual astronomy to the professionals. And this person who wrote this book is an uber, one of the top brains in astrophysics and in particle physics, ever maybe. So who's to blame? For any correct information, Steven Weinberg, the first 3 minutes, A Modern View of the Origin of the Universe, the updated edition, was 1977, 88, and 93, the various publications probably associated with errata and with, just updating the science. For any mistakes, I will take full blame for the mistakes, so you can put that firmly on my shoulders, not Dr. Weinberg's. What are we going to cover tonight? We're going to talk a little bit about the author, why we should listen to what he has to say, a quick review of some science concepts, expansion in redshift, the cosmic microwave background, a few select moments in time, what happened when, and then some afterthoughts with actually a very recent update. So stay tuned for that last little bit. That's kind of cool that we can see science actually happening. In our current life experience. It's kind of neat. Just so we Oops, I'm hitting the wrong button here. Expansion in redshift and cosmic microwave background. We're going to go into these concepts in a little details, but I want to warn everyone, don't get lost in the details. The argument for the Big Bang Theory is very simple. There's only two things that they're arguing, and they're very simple to follow. The details, of course, are very detailed and very scientific. However, don't worry about the details, just worry about the argument. Why do we believe the Big Bang is the Big Bang? Well, it's just two things that are pointing us in that direction. All right, a little bit about Steven Weinberg. That's how he wrote his name as the author of this book. So he is a doctorate and has done lots of awesome research, won the Nobel Prize, a whole bunch of things. So all the honorifics belong to this gentleman, but I'm just using his name as it was on this book. Here he is right here. Oops, again with the here he is right here. And this is him with a group of other Nobel laureates with Queen Beatrix of the Netherlands. Queen Beatrix of the Netherlands. So amongst august company. A very abbreviated list of Steven Weinberg's professional achievements. Got a bachelor's from Cornell University in 1954, a PhD in physics from Princeton in 1957. He has done original research in theories in particle physics and physical cosmology. So that means not only in the really little stuff, but in the really big stuff too that you see out in the universe. He shared the Nobel Prize in Physics with Sheldon Glashow and Abdus Salam in 1979, and I pardon any mispronunciation. Numerous other awards in the sciences and for science advocacy. He was a researcher, faculty or lecturer at Columbia, Berkeley, MIT, Harvard, and the University of Texas at Austin. He has 15 books on science, science communication, and science philosophy, and multiple scholarly and popular articles. So maybe someone we should listen to. Has a couple of things that he's done. All right, so yay, let's review some science concepts, and I promise almost no equations. It's 100% guaranteed, and you get your money back if we do too many equations. All right, so a little bit about particles. This is a picture of a particle bubble chamber. The particles got created and zoomed off in whatever direction they wanted to based on their charges and other properties. And this is a picture of the inside of the Large Hadron, well, the building or the enclosure of the Large Hadron Collider. All right, so things to remember or keep in mind about particles and particle physics. Particles that move fast enough when they collide will overcome intranuclear forces, the stuff that binds the particles together, and are annihilated. New particles are then created from the resulting energy. So I thought, and maybe a lot of you guys think, that when a particle accelerator works and two particles bang together, that the shrapnel from that collision is what we are capturing and measuring. That's not what happens. These particles are hitting and completely disappearing into energy, or getting completely converted to energy. There's no particles, just energy left. Then from the energy they recondense into particles. So new particles are created from the energy that was developed during the collision. That's a very interesting understanding of these particle accelerators. A particle's rest energy is given by this very famous equation here, E equals mc squared. Particles are created in matter-antimatter pairs. The photon is a particle with zero mass. It mediates the electromagnetic force, right? Photons are associated with light, is basically what that's saying. Electrons are leptons and are small with small mass. We know what electrons are from maybe our chemistry classes. Protons and neutrons are baryons made up of quarks. They are larger and more massive than electrons. So leptons are a thing themselves. Protons and neutrons are a different type of matter and have a smaller piece that they're made up of called quarks. Neutrinos are also leptons, so they're the same like electrons. They're their own thing, and they react with baryonic matter only extremely weakly. All right, don't worry about all that stuff, but just a quick review for when we use these a little bit later, that these are real things and those are some of the principles. So let's also remember that particles behave weirdly. This is called the Young's double slit experiment. And what's happening here? Light is getting shown this way, hits a double slit, and instead of two a pattern of two things where the slits are, we get these wave patterns. So particles can behave both like particles, but also like waves. And they're not really behaving separately from each other. They sort of exist as both. Furthermore about light here, let's talk about redshift. This is a spectrum of a gas. Light is shining through it, and the gas isn't currently moving forward or away from us. A redshifted spectrum would move away from us. It has the same pattern, but you can tell that everything is moved to the right. So that same pattern, that absorption pattern, moved to the right a little bit towards the red, and so it's therefore called redshifted. And the blue shifted spectrum will move to the left towards the blue and be blue shifted. That's moving towards us. Very similar to a train, right? When a train comes at you, you can hear it coming, and it goes wow when it passes you, right? That's the wave nature of sound. The same way this red shift and blue shift is the wave nature of light. Furthermore about light. Light can behave both like particles and waves. We just said that. Light from objects in space can be collected and analyzed. That's how we know about all that stuff that's so far away. We can't visit all that, most of that stuff. We can visit, so far we've visited like 8 objects, right? We can't visit all the stars. We can't visit any of those things. The only thing we know about them is the light that has made it here. Their spectra and apparent luminosities can be directly measured. Similar to sound waves, light is subject to the Doppler effect. That's the red shift and blue shift. Redshifted light is lower frequency, longer wavelength from objects moving away, and it's less energetic and therefore cooler. Blue shifted light is higher frequency, shorter wavelength from objects moving towards us. Visible light is a small piece of the entire electromagnetic spectrum, which includes from gamma rays all the way to radio waves. The fastest anything, including light, can travel through space in a vacuum is c. That famous constant in E equals mc squared. That's the speed of light, which is around 300 million meters per second, or approximately 671 million miles per hour. Pretty darn fast. Well, let's see, what did I want to say? Oh, yeah. Things like light, things that don't have mass, not only can they travel at the speed of light, they must travel at the speed of light. That's the only speed they can go. Expansion and redshift. All right, this is chapter 2 in the book, the expansion of the universe. What are these things called? Yes. Galaxies, very good. Where did we get these pictures? I took them here at UACNJ. We can take these levels of pictures here, anywhere, basically anywhere now, where the light conditions allow us to do it. All right, so this is the Whirlpool Galaxy, the Cigar Galaxy, Triangulum. This is the Whirlpool. This is a bonus material. You might see here these two galaxies are the same. The Pinwheel Galaxy, you can see the center. You can see this bright star here, which is this bright star here. This bright star here, which is this bright star here. You can see this bright star, which is not here. That was actually a supernova in the Pinwheel Galaxy a couple of years ago, and I was lucky enough to take a picture beforehand and afterwards. So kind of cool that I was just fooling around and caught a not anything like real astronomers. They caught it as soon as it appeared. I was like a week or so after they did, but kind of cool that I caught that. We didn't always know what galaxies were. As the young gentleman here mentioned, that was obvious to all of us, most of us, if not all of us, that those are galaxies. But we didn't always know what they were. In 1750, Thomas Wright proposed that the Milky Way was a flat slab of stars in which our solar system resides. And way back then, you have to kind of remember that scientists who made proposals like this were risking life and limb when they made proposals like this. So these are brave individuals making what many people thought heretical or preposterous suggestions. All right, so kudos to these brave women and men. In 1775, Immanuel Kant proposed that some nebulae that astronomers observe are actually circular disks like the Milky Way. So it wasn't that we discovered galaxies, we saw them in the sky with the telescopes of the time. We just couldn't imagine that they weren't part of our local surroundings. Though widely accepted, Kant's ideas of a universe full of galaxies was debated for the next 150 years because scientists don't rely on, I think it's this, right? They need what? Evidence, right? So the whole idea was, are they really galaxies? How do we figure out they're galaxies? How far away are they? All these, how big are galaxies? What are these things? And how do we go about understanding them? In 1923, Edwin Hubble observed Cepheid variable stars in Andromeda. And using previous work from Henrietta Swan Leavitt and Harlow Shapley, proved that Andromeda was its own separate galaxy and not a nebula in our Milky Way. So finally, there was data. And there was mathematical calculations and proof that galaxies are real and they're very far away. Hubble's original estimate of approximately 1 million light years away, that was his original estimate. Our modern estimate is it's approximately 2 million light years away from us. Light year being, of course, not a measurement of time, but a measurement of distance. So what does that mean? Well, astronomers weren't sitting around waiting for galaxies to be proven and discovered that they were not just nebulae, but something completely different, not in our neighborhood. Since the mid-19th century, and among many other things, astronomers had been measuring spectral shifts of astronomical objects, including the previously suspected, now confirmed galaxies. So that's where the redshift comes in. They measured how far it was away from us by the color of the light. It was quickly noticed, with only few exceptions, that all galaxies are redshifted. Hubble announced in 1929 that he discovered that the redshifts of the galaxies in all observed directions increase roughly in proportion from their distance to us. So the further away they are, the faster they are moving away. Remember, redshifted means that it's moving away from us. The further away the galaxies are, the faster they're moving away. This became known as Hubble's law. It's accepted as current thought that the value of Hubble's constant is between 67 and 77 kilometers per second per megaparsec. You don't have to worry about the numbers, but it's a measurable constant. But again, this is a very simple concept. All galaxies, everything in the universe is moving away from each other. Anything that isn't gravitationally bound to your current galaxy is moving away from you. Doesn't matter what galaxy you are, everything's moving away. This is Hubble's plot of data, actual data. So what is the implications of all that? The galaxies are moving away. We can measure it. This is the data. What are the implications? The universe is not static. It's currently expanding. If everything everywhere is moving away from each other, that means the universe is getting bigger and bigger and bigger in every direction. no matter where you are. The universe is homogeneous and isotropic. That just means it's kind of the same things are happening everywhere. It doesn't have different physics in different locations. And isotropic, sort of the same. Sort of, it looks the same in every direction. This is called the cosmological principle. We can now play, knowing this information, we can now play with the time coordinate in our minds. All right? So if this is the universe now with everything moving away, that means if we were to scroll back time, what does that mean about everything in the universe? It was closer. Okay, let's roll the time back a little bit more. It was closer. Let's roll it back a lot more. It was a lot closer. Let's roll it back. And now we can calculate based on the observations of how fast things are moving away and how much time we go back. We can calculate to where everything was really, really, really close. Like impossibly close. Let me finish keep that thought. Dr. Weinberg introduced Friedman's critical density and wrote about the universe's fate. So that's what happens if we fast forward it very far. But if you hit the rewind button, just as I was saying, hard and long enough, almost all the way back to the beginning of time, you can see that all things must have been a lot closer than they are now, just as I had described. Not just a lot closer, but a lot closer. No, really. Really close. Not normal close, like weird close. And that's why we went into particle physics. Particle physics close. And from an infinitesimal and hypothetical point, remember geometry, point doesn't have length, width, nor height, right? It's just infinitely small. Well, from that infinitely small point is when maybe it all started. We now call this theory the Big Bang. So, very simple explanation, right? If things are getting bigger, at one point they must have been a lot smaller. And, you know, if you bring the time back far enough and do those calculations based on what we know and how fast things are moving, then it must have been really close a certain amount of time ago. And they did that calculation. 13.8 billion years ago, right? All right, so that's one prong of the argument, and a pretty compelling prong. But, you know, this is science. We're not going to just stop at one, right? Let's go for another one. The cosmic microwave background. Did you know that theoretical physicists predicted the cosmic microwave background over 10 years before its discovery? Because you might have heard of the discovery of the cosmic microwave background, but what you might not have known is that it matches a theoretical prediction prior to it being found, which means that they matched in two separate methods of inquiry, which makes you believe it a lot more, right, than somebody said it and then they pencil whipped some sort of theory into place afterwards, right? That's not what happened. What happened is they had a theoretical prediction and then they ended up getting data to confirm the prediction. So a lot more compelling. It was postulated from exploring the particle physics of the early universe. However, they did not predict that its importance would be as predictive as it was as corroborating evidence of the Big Bang theory. So experimental verification ended up lagging once they made this prediction. They didn't run right out and start trying to find the cosmic microwave background. They didn't know how important it was to the actual argument. Okay, so once upon a time in New Jersey, but not these guys. A good show, but not these guys. It's these guys. And who are these guys? I actually, so I can identify who's who. Wilson is the guy on the left, and Penzias is the guy on the right. Arno A. Penzias and Robert W. Wilson worked at Bell Labs in Homedale, New Jersey. So yay, New Jersey, right? They were commissioning a radio telescope for the survey of the Milky Way. They were troubleshooting sources of noise in the signal from the receiving the system. They had no idea what they were finding. They were just troubleshooting. What's this noise we're hearing? They were measuring in the microwave length at 7.3, the microwave, wavelength at 7.35 centimeters. They found a stubborn source of noise that didn't depend upon where they pointed the equipment or time of day. Famously, they were cleaning pigeon droppings off of the equipment and things like that to find the source of this noise. And they found a stubborn source of noise. The signal corresponds to the excitation of electrons in a closed thermal system at temperature of 3.5 degrees Kelvin. This is referred to as a black body temperature. The 3.5 degrees Kelvin is the important part of that sentence. They were looking for a black body of this temperature, or they were finding a noise for that black body at that temperature. Through colleagues, Penzias and Wilson were put into contact with the physicists of Princeton who had developed those prior theories about leftover radiation from the early universe, and were starting to set up their own experiments. Those physicists are P.J. Peebles, Robert Dick, P.G. Roll, and D.T. Wilkinson, and those were the ones that I'm aware of, but there may have been probably a lot of other people involved. Penzias and Wilson had found this theorized leftover radiation, and they won the 1978 Nobel Prize for Physics for their discovery. Not the theoretical physicists, but them for discovering it, but, pretty big discovery. But what is the cosmic microwave background? We found that interesting thing where they found it and all that type. I mean, we've talked about that interesting thing where they found it. Why is it important? Well, after the Big Bang, the expanding universe was very hot and very dense, soup of radiation and elementary particles. Matter did not exist as it does now. Remember, E equals mc squared, and matter at a certain energy level, if it's above that energy level, it can't exist. So it was so energetic in the early universe that particles had not existed yet. Many particles, most particles. Even though the universe was expanding rapidly, the mean free time between radiation particle interaction was unimaginably fast. Radiation couldn't go anywhere. That means, for instance, it takes 10,000 years for light to travel out of the sun. That's because think of it like Plinko. It was bouncing around so fast amongst the particles that it couldn't get out of that it can't get out of the sun. So 10,000 years is the mean free path of light coming out of the core of the sun. Okay? But in this instance, the universe, the entirety of the universe was so hot and so dense, light just could not escape yet. The radiation and particles were in thermal equilibrium and behaved like a black body. The universe then cooled in thermal equilibrium until it reached around 3,000 degrees Kelvin. Then electrons bound to atomic nuclei and regular matter formed. Once that happened, the universe's density dropped and it became transparent. So no light. It couldn't get out. Then all of a sudden, the universe got cool and the energy levels dropped to the point where light could now travel freely. Light could go. And the universe continued to expand. The wavelength of light expanded with the rest of the universe. It is redshifted and therefore cooled. So that light that originally popped as soon as the universe was cool enough started cooling as the universe expanded, down to, guess what temperature? Right now, it's that black body radiation we see is at about 2.725 degrees Kelvin. So that is the cosmic microwave background. The light that originally got loose from the universe when it cooled, freely traveling, and is now at this temperature, and we can see it. So we can see, Brian Cox famously say, I have to attribute this to him, we can see the Big Bang. We can see the light that was released from the Big Bang. So that's the two arguments. The expanding universe, that we can say this will happen in the future, and this is what happened in the past because we can play with the time coordinate, and the fact that we can actually still see the light from the Big Bang. Two very simple arguments. The science is really cool and very detailed, but still simple arguments. This is the black body curve. This is, in fact, is the black body curve. And black body just means that it releases heat based on its temperature, not on receive and being only radiating heat from its temperature, and not reflecting anything really, just radiating heat from the energy stored within the body. This is an actual picture that we've done surveys. We, meaning humanity, has done surveys of the sky, and that is the cosmic microwave background right there. So let's talk about what happened when. We start somewhere very soon after the Big Bang. There's no theories that say the Big Bang was from the Big Bang theory currently begins just after the proposed singularity. All right, they're not sure whether it was a singularity, whether it was just a vanishingly small object that just got smaller and smaller and smaller the further you went back in quote-unquote time. Our Big Bang, our current theory, happens just after the expansion began. The temperature in the universe is 100 billion Kelvin, pretty hot. The universe is a soup of matter and radiation and is in the state of thermal equilibrium. The only matter that exists are the electron, the positron, neutrinos, and antineutrinos, and the photon. The density of the universe is approximately 3.8 billion times of liquid water. Let me just check and see how much time I'm, all right, doing good. All right, 0.11 seconds have elapsed since the beginning of the universe. The temperature is now only 30 billion Kelvin. The universe is still a soup of matter and radiation and is in a state of thermal equilibrium. The only matter that exists are the electron, the positron, neutrinos, antineutrinos, and the photon. Free neutrons and protons are being formed, but it's still too hot for them to be stable, so they get blasted out of existence. Their ratios start to differentiate between 38% neutrons and 62% protons, and that's important, and we'll go into, as we get to the end of the play, why. And the density of the universe is approximately 30 million times that of liquid water. 1 second, or just over 1 second, have elapsed. The temperature is 10 billion degrees Kelvin. The universe is a soup of matter and radiation, as in a state of thermal equilibrium. The universe becomes transparent to neutrinos. This isn't light yet, but just see, it's in red for a reason, that it becomes transparent to neutrinos. Free neutrons and protons are formed and blasted out of existence. The ratios differentiate excuse me, to 24% neutrons and 76% protons. The density of the universe, you can see, has really dropped off now, and it's only 3,800,000 times that of liquid water. You know, still very, extremely, amazingly dense, but nowhere near as what it was. Almost 14 seconds have elapsed since the creation of the universe. The temperature is 3 billion degrees Kelvin, still kind of toasty. Electrons and positrons are stable at this temperature. They begin to annihilate each other. So now we have stable matter. Neutrinos previously freed are cooler than the rest of the universe, so they started cooling earlier than the rest of the universe did. The balance of neutrons to protons is now 17% to 83%. And if there are any chemists out there, they might start to see the significance of those numbers. Some stable nuclei can form helium, and atomic weights above helium are still suppressed. They still can't form because they don't have the required ingredients to form stable nuclei yet. It's just not cool enough for those particular particles, if that's an expression, for them to coalesce into a proton. 3 minutes, 2 seconds have elapsed. The next tick. The temperature is only 1 billion degrees Kelvin. Electrons and positrons are mostly gone. The universe now consists of photons, neutrinos, and antineutrinos. Mostly gone. Thankfully not fully gone. The balance of neutrons to protons is 14% to 86%, and now we're getting really close to an important ratio. Some stable nuclei can now form. Helium nuclei can form but are suppressed because deuterium, which is a necessary precursor, if you, again, if you are into chemistry at all, you know mechanisms are things, and the mechanism to create helium just quite isn't there yet. So helium is not yet stable. Well, deuterium is not stable, and therefore helium can't form. Approximately 3 minutes 46 seconds have passed. This is our intermission in this play. Deuterium nuclei are now stable. Helium nuclei form at a rate of twice that of available neutrons in the universe, 13% neutrons to 80% protons. And now we can know that that is why we have the ratio of hydrogen to helium that we have in the universe. Okay, so another piece of evidence. The particle physics predicts this creation of hydrogen and helium. The temperature is about 90 million degrees Kelvin. Helium nuclei, of course, have to have 2 neutrons associated with them, which is why that's important. Tick. 34 minutes and 40 seconds have elapsed since the creation of the universe. That was a busy 30 minutes in our universe's history. The temperature is 300 million degrees Kelvin. Electrons and positrons are gone except for 1 part in 100 million. Again, that's important because we exist and we're made of matter. So guess what? Which one? Matter or antimatter? Matter won. And that's, but of course, if antimatter, we might just all be sitting here and we'd just all be made up of antimatter instead of matter, right? So who knows? But the point is that not all matter and antimatter destroyed each other. There was an asymmetry. There was more matter than there was antimatter in the creation of the universe. Nuclear processes have now stopped in the universe at large. Nuclear particles are bound in mostly hydrogen or helium nuclei. It's actually still too hot at this point to form stable atoms, but the density of the universe is now only 9.9% of liquid water. So we went from, did I put it here? We went from, the last we said, 380,000 times the density of liquid water to only about 10% of the density of liquid water in a matter of minutes. Now the lights fade on our little play here. Not much interesting happens for 700,000 years, but the temperature drops below 3,000 Kelvin. Stable atoms are now possible. Free electrons and atomic nuclei begin to pair up and make happy little atoms, Bob Ross style. And then the universe becomes transparent to radiation. So there is your cosmic microwave background. That's what they calculated. That's what the theory said. Stars and galaxies begin to form from that matter, and then, nothing much happened. Another 10 billion years or so go by, and Dr. Weinberg writes his book, The First 3 Minutes. So, kind of cool. Everything happened really fast, though, right? That's why you need the particle physics to understand any of this. All right, some afterthoughts. The cosmic neutrino background, as predicted, 1.75 K. Remember we were talking about that first red, let's see if I remember how to do this. That first red slide, this one right here. The universe became transparent to neutrinos. Well, if that's true, and it started cooling faster, then there should not only be a cosmic microwave background of light, there should also be a cosmic neutrino background. All right, let me see if I can find out where I was now. Yes, there is a cosmic neutrino background. They found it at 1.75 degrees Kelvin. Because it came out earlier, it cooled faster than everything else and is therefore now cooler. So more corroborating evidence. The cosmic inflation, the CMB. Just want to say about cosmic inflation, there's some additional discussion Dr. Weinberg did about cosmic inflation. One of the interesting things is that during cosmic inflation, remember when I said you can't go faster than the speed of light? You can't travel through space through the speed of light. Space can expand faster than the speed of light because space isn't traveling through space. Space is space. And so during the inflationary period, it traveled faster than the speed of light, or got bigger, at least to the way we measure. Before the Big Bang, there is conjecture about what the Big Bang was before the Big Bang. The question doesn't compute with our physics. So the scientists speculate. You know, it's fun to think about it, but they're not scientifically interested in what happened before the Big Bang because there's nothing we can do to penetrate the fact that we don't have science to explain what happened before the Big Bang. There's just nothing that we can do currently, I guess. Maybe there'll be something, but there's nothing that we can do to use science to sort of penetrate that mystery. Matter antimatter asymmetry. I talked about that. For some reason, there was more matter than created than antimatter. Remember, matter and antimatter are created in pairs, equal pairs, and if they meet again, they destroy each other. And that's what happened largely in the creation of the Big Bang. Then why are we here? Why is there matter? Right? Because there was an asymmetry, and luckily, since we all are standing here, it existed. But there's more news to come on that one. Dark matter and dark energy are hot topics. We're aware of that from the news, if nothing else. Dark matter being something is holding galaxies together that we can't see. We don't know what it is. Dark energy, the universe is expanding. Not only is it expanding, but it's accelerating as it expands. So that means something's pushing it. And what's pushing it, we call dark energy. And then the heat death. We talked about rewinding the time clock all the way back to the beginning of the universe. But what happens at the end of the universe? The heat death is the current preferred, or one of the preferred theories of what happens if you don't rewind it but fast forward it. And this is, scientists have since revised the timings a little bit since Dr. Weinberg wrote his book. This is the current timing and what the current theory looks like, what happened when. And for anyone who reads the news, sometimes you get those kind of science news reports. Didn't the JWST, the James Webb Space Telescope, didn't it disprove the Big Bang? Some places, some reports reported that it disproved the Big Bang. No. There was some early identification of anomalous results relating to the size of early galaxies, but that's a feature of science. That isn't a problem with science. These anomalous results were reported, and other scientists looked into it. All right, all scientific data should be reported and reviewed by the fellow scientists in the field. That's how we learn. We don't keep it secret nor have our own special little theories. They are shared equally, and experts are allowed to comment on your results of the science. You should remove ego, at least from the data. It's not, I'm not saying that scientists don't have egos. They do, but you should remove, as a professional, remove the ego from the results and from the data. The size of the early galaxies originally estimated were incorrect. The mistake had to do with light extinction and the application of photometric versus spectroscopic redshift, both technical things, but how you measure the redshift, which we talked about, and also about what's called light extinction. If we measure the light coming to us from a star, we can't assume that there's nothing in between us and the star, right? Or from between the galaxy. If some shady material is between us and one of those objects, that's called light extinction. Okay, the light is gotten extinguished a little bit between the distance, and you have to measure or estimate that in order to understand the true value of the light coming from that source. Current estimates of the early galaxy sizes fit the CDM, the model of galaxy formation. And some of these reports came from somebody who has long had a problem with the Big Bang Theory. So I included these two sources to help combat motivated reasoning. Harry Frankfurt, a philosopher, wrote a good small little paper. It's like a mini book on falsehoods called "On Bull Stuff," but you can see the asterisks, adult people, to understand what the title really is. And Skeptics: A Guide to the Universe, which is a podcast a little bit about identifying conspiracy theories and other type of motivated reasoning. All right, recent events. So we talked about the proton and the neutron, and the proton and neutron are made up of these smaller particles called quarks. Very good. The proton is 2 up and 1 down quark. The neutron is 1 up and 2 down quarks. Excellent. Who said quark? Very good, sir. This is the standard model. The quarks are here. The leptons are here. The neutrinos are here. And these are the bosons. Don't worry about it. It exists. Looks a lot like the periodic chart, but it's quote-unquote the periodic chart for particle physics. Recent events. As reported by Matt Dowd on PBS Spacetime, that's where I found it. There was an announcement on March 25th from 2025. This announcement is about a finding that is unpredicted by the unmodified standard model. Baryonic matter, that's these guys, the type of matter that we're familiar with, protons, neutrons in the nucleus of an atom. Amongst other particles, there are other baryons. They're comprised of 3 quarks. Mesons are a quark-antiquark pair. The protons are, as we said, 2 up and 1 down, and neutron is 1 up and 2 down quarks. 2025, they announced the discovery of beauty baryon asymmetry, which is CP symmetry violation. Without the theoretical knowledge from the Big Bang that there is some sort of asymmetry, for some reason there is more matter than there was antimatter, they have actually identified in the lab, naturally occurring, nothing to do with the Big Bang, well, something to do with the physics of the Big Bang, but nothing to do with our discussion of the Big Bang right now. It announced the discovery of beauty baryon asymmetry. So CP symmetry violation. Asymmetry actually happens and is reproducible. So another Big Bang prediction come to light. This was found at the LHCb experimental site at CERN. It doesn't explain fully asymmetry, but hints at that there are further physics to discover that probably can explain or may eventually explain the matter-antimatter asymmetry. And there is, of course, all sorts of now continued research into baryon, lepton, and neutrino asymmetry. So they just started to crack. They don't have a theoretical physics full explanation of what's going on. There are some proposed explanations, but they don't have a agreement on it yet. Yet we've reproduced it, and it's actually a thing. So it's not something to hang your hat on. The Big Bang is bunk because of this asymmetry. No, this asymmetry seems to be actual thing that is naturally occurring. So kind of cool that just this year we found this new information at the Large Hadron Collider, and yay big science on some of this stuff, right? So I urge everyone, the Big Bang Theory here, you can learn more about it and see some of the cool things about the life in our universe, the lifetimes of things in an astronomy club. Stay safe, everyone. Enjoy your evening. And that is my presentation for today.
All right. Thank you, Paul, for another great presentation. Thank you, everyone who's joined us not only here but online. So we are going to do a question and answer session now that he's done with the presentation. How that's going to work is people here, you're going to raise your hand and then wave it about a bit, because I'm like the Jurassic Park T-Rex. My vision at night is entirely based on movement without my distance glasses. And it's kind of dark because it's cloudy and we have like a quarter moon. So you kind of just are shadowy figures in the dark to me right now. Like I said, raising hand, waving about. Online people, you have it easy. You just get to type in chat, and which is part of why I'm night blind, because I've been looking at electronic devices for online chat. Just a brief reminder, if you need to use the restroom, that is the porta potty in back. We do have an observatory open, so you will be able to at least see a telescope, if not look through it, because it's still very cloudy. And like I said, there is a museum and gift shop that I will be manning after the talk. So I'm going to start it off with our first online question, which was, if you could have any job in astronomy, what would it be? Like an astronaut, one of the ground crew, mission control, scientist, developer, whatever.
Yeah, I think I'd be probably more oriented towards the mathematical side than the action side. It takes, I mean, all our astronauts are very well-educated science, but also have that co-pilot, renegade not crazy person, but adventure, high adventure instinct associated with it, which I don't have as much of as maybe they did. But I would probably go for something a little bit more mathematical and interesting. Cosmology seems really interesting right now, so I would probably ponder the secrets of the universe at large more than be a line astronomer. So, but yeah, all
Not
that
not the
stuff.
type to jump out of a perfectly
Uh,
good working airplane, are
no,
you?
or no, not jumping or going to a different planet, and dealing with. I get frustrated when the installation of my new HVAC system doesn't go right. Just imagine that, on a different planet. So
At least here you could get
take
spare parts.
takes a different breed of person to do that type of stuff. But no, seriously, the cosmology seems very interesting, and maybe I would have done something like that if I chose that field.
Right. I know there was a question out here earlier, but I lost track of you because, like I said, you're all now shadowy figures in the dark. But now is the time to ask that question if you remember. Right.
Okay, it wasn't me, but do I have to do anything?
It's already on.
So you mentioned that galaxies are moving away from each other and they're doing it at increasing speed.
Yes,
But I thought I heard that the Milky Way was merging with Andromeda
you
or
are
something.
not wrong at all. In fact, but I want to remind you.
So how does that happen?
Yeah, exactly. Uh, I think I did make the exception. If I didn't, please note it now. That anything that's gravitationally bound, anything really that's in the local group of galaxies. Remember, galaxies are called the local group, the group, various other designations of galaxy clusters, right? Anything in your local group is gravitationally bound to you. Anything that gravity overcomes the expansion of space. So anything that the gravity's really, the reason Andromeda and the Milky Way galaxy are closing in on each other and will eventually collide is because the gravity is that we're close enough to each other that the gravity is pulling us together. Gravity further away, in other words, the amount between the distances between clusters of galaxies, everything that is not gravitationally bound to us is expanding away from us. That is by far, because there's trillions of galaxies in the known universe, right? And we've only got 50 galaxies in the local cluster, or whatever the number is. Could be hundreds, but it doesn't matter. It's tiny compared to the rest of the galaxy. So most of the universe is expanding away from us. There's a few galaxies that are gravitationally bound to us.
All right. And was there another question out here? Bueller. I know most of the crowd's too young to get that joke. But it is a good movie for when you're old enough to actually watch that movie. So our next online question, and people online, if you do have a question, do get that in now. And I say this just because stream delay is a thing. By the time they hear that, we're already a couple minutes into the future. Would things be much different if antimatter had won, or would our antimatter just be their matter and our matter be antimatter to them?
Yeah, well, obviously, if things were different, they wouldn't be the same, right? So, beyond being pithy, what that means is the universe didn't have to. Well, the believing depends upon how much you believe how deterministic what has happened so far was. However, if antimatter won instead of matter, we could quite possibly never existed as humans. We could have different physics depending upon how particles interact and all those type of things. So it could have been very different. It could be that there was another civilization just completely made of antimatter instead of what we would call matter. However, they would probably call the antimatter matter, and what we are currently made of antimatter, right? So it all again it depends upon perspective too, if you really want to tickle your noodle about that one. So it's a good question, and it's good but like I said, it's not as pithy. If things were different, they wouldn't be the same. There could be significant difference, a whole universe full of difference.
I don't know. I could have used evolution to have given me a couple extra arms. I never have enough hands. All right. Question. Was that a hand raise, or was that just waving about? Like I said, I'm kind of blind. All right. So it looks like our questions have come to an end. I do want to thank you all for joining us here and online. Do check us out on our website, uacnj.org. We are a nonprofit. We do this for free, and any donations that you make do go to keeping our bills paid, our lights off, because we're astronomy based, as Dan keeps lecturing me about. You cannot keep the lights on. That's light pollution. So we do thank you guys for keeping us alive. Okay, that was just more flailing. For those of you online, do hit those like and subscribe buttons. The completely free actions. It does help us out a lot. And with that, everyone have a great night. Clearer skies than we've been having on these Saturdays, and good seeing.
And there is observatories open over there, so I don't think they're showing anything, but you can at least see what a permanently mounted larger telescope looks like. Thank you, everybody.
Yeah, right now we just got the permanently visible cloud nebula, earthbound.